Okay, my name is Changzeng. Uh, um, Now I will introduce my research. The topic is dynamic mini three-board bending experimental technique, which computed by me and my tutor, Professor Zejian, my colleague Zhicheng. I'm from the Beijing Institute of Technology. The contents have five aspects. Part one is the risk background and significance. Engineer structure and engineer materials such as the hazardous steel and ceramic which used to the aircraft and the target and car and tank and so on. It is widely subject to the dynamic loading and so to avoid the occurrence of the dynamic fracture under the impact loading, so we need a dynamic fracture criteria. So Mode 1 fracture toughness, Mode 1 fracture is the most easy fracture mode. So I will introduce some current status of research for Mode 1 dynamic fracture mode. There is two aspects. First, one is from the improved apparatus point of view. Costing is the first person. The dynamic tensor apparatus is used to measure the Mode 1 dynamic fracture toughness. And with the development of the technology and science, there is the 1 bar 1 point bending and 1 bar 3 point bending and 2 bar 3 point bending and 3 bar 3 point bending and 2 bars 4 point bending. It's one aspect. On another hand, from the improved speed configuration aspect, just like the dynamic wedge technology and the Brazilian disc brakes. Okay. So, but there is a limitation in the existing experimental method, just like the material selection. Most limited to the brittle materials, and the second is the calculation of the stress intensity factor needs to satisfy the force equilibrium equation, and three diffusion effect and the transmission signal cannot be obtained directly, and the large size makes it difficult to crack initiation and or even expand. And then finally, the loading rate cannot be precisely controlled. Based on this, so I will introduce my research route. Firstly, I will we design the Mode 1 dynamic fracture method and validated the first step 2. I will use the experimental inertial method to determine the dynamic stress impact intensity factor, and the stream method is used to determine the correct initial time. After the test, we can carry out the macro analysis, just like the loading rate effect of the dynamic fracture toughness between the QC static and the dynamic fracture toughness. And the failure process of the materials or structure is captured by the high-speed camera. Finally, the macro analysis is used to analyze the microstructure evolution of the fracture, which is to find the failure mechanism of the materials. So I will introduce the Model 1 dynamic fracture method. In my work, I've compared the different loading ends and the different specimen geometrics. So finally, we totally the Model 1 dynamic fracture method is obtained. So the verification is I calculated the DSFF curves on the Model 1 and Model 2 and Model 3 modes. And the results show that the DSIF values for Model 2 and Model 3 are totally 0. So which it means that the proposed method is satisfies pure Model 1. So you see, this is a schematic the Model 1 dynamic fracture method, and the real apparatus, and this is specimen. Yeah, this is the specimen. This method has 4 advantages. First one, direct acquisition of transmit signal, and the specimen satisfies place G condition, and process control the loading rate, and finally, the small specimen size for easy fracture initiation. In this method, the key of this method is the experimental number method. So I will introduce it. Firstly, this is the original waveform. We use the incident stress as the input quantity to apply the end of the incident bar, and in the simulation we use the elastic model to carry out the mechanical behavior of the bar and the specimen. And the mesh refinement is used to obtain the precisely the predictive displacement field, and then submit this function, we will get this, the DSIF curves. Okay, and it should be noted that the string gauge method is used to determine the correct initiation time. Let's see, show this picture. This is the start point of the loading, and this start point is the fracture initiation time. The difference between 2 points is the correct initiation time. Okay, this is the Model 1 dynamic fracture method. I will introduce the dynamic fracture features of the 2 styles. To compare the loading rate effects of dynamic of the fracture toughness, we test the QC static fracture. And so this is the fracture morphology of the 13 CR. And there is the 2 region. Yeah, the region A is nearly the correct tip. So this there is a ductile fracture, such as the dimple and the bright shear bridges. And in the region B, this is the QC cleavage fracture, such as the fan-shaped river pattern and a second crack. And for 14 CR, in the region, it's similar to the 13 CR. It's just a ductile fracture, which characterized by the dimples. And in the region B is different. It's intergranular fracture. In the there is inclusions as the green arrows and secondary cracks. And this picture shows the in the over a wide loading rate, the fracture toughness of the two steels show the have a positive relationship with the loading rate. And using the scanning electron microscopic technique, we can analyze the failure mechanisms. And the for two steels, both materials show the QC cleavage fracture morphologies features, just like a dimple rear pattern and a secondary crack and cleavage plate, as well. And this picture shows the failure process by the high-speed camera. And in 17 microgram, the like initiate. And to deeply understand the loading rate effect, I do some comparison for different materials. For 13 CR, it can be seen from the two picture left picture. The secondary crack increased in size and number with the increasing loading rate. And moreover, bacterial shell ridges increase in number, or provide a reasonable explanation for increase in fracture toughness. And for 14 CR, there is same to the 30 CR is just like the secondary crack. And the increase in fracture toughness may be due to the increase in the critical QC cleavage stress with the street rate. So that's the dynamic fracture features. Part 4 is the dynamic bending features of the cinematics. The proposed Model 1 dynamic fracture method is still used here and to measure the dynamic bending stress of the ceramic. This equation is used to measure the dynamic bending stress, and it should be noted that the strigos is still useful to measure the initial fracture moment of the materials, and the theory is the same for this. This picture shows the bending stress of the zirconia have a positive relationship with the loading rate. And this picture shows that the crack initiation time decrease with the loading rate. The fracture morphologies of zirconia show the two features. Red is the transgranular fracture, and the yellow is the intergranular fracture. And by comparing these two, the two picture under the lower and the higher loading rate, it can be found that with the increasing loading rate, the failure mode changes from a mixed transgranular and intergranular fracture mode to the transgranular fracture. Okay, finally, we will introduce the conclusion. In this work, I proposed a pure Model 1 dynamic fracture method and use it to measure the dynamic fracture toughness of the two steels and dynamic bending stress of the ceramic. And it should be noted that the string gauge method is useful to measure the crack initiation time for the Model 1 dynamic fracture or model or dynamic bending. And and I show the loading rate effect of the dynamic fracture toughness and the dynamic bending stress. And it should be noted that the fracture toughness depends on the energy expended in the formation of the two types fracture regions during the fracture initiation time. Okay, thank you for your attention.